Well, I had to sneak in an extra joke. Found this cute cartoon. My hobby extrapolating. So we have number of husbands graphed per day. And he says, as you can see, by late next month, you'll have over 4 dozen husbands. Better get a bulk rate on that wedding cake. And we will be talking about extrapolating. So first of all, what is extrapolation? The linear model below works really well from 1900 to just before 1950. So we're looking at a men's age at his first marriage. So you can see in 1900 it's about 26, and it's getting younger and younger, and we get to 1950. So if I just use this data, I would probably guess that someone down in this area, we'd be getting down to 23 years old, and just keep going down, right? Well, I'm going to go ahead and extrapolate and use the model to predict what would happen outside of this range of data. So this is the range of data used to create the regression. Now let's see if we can use it over here. Well, can we use it to predict the future? And you can see actually the ages started dipping really fast right here. And part of that reason was, well, World War II happened and people were getting married a little earlier because they weren't sure what was going to happen when they went to fight in the war. And so you can see actually a sharp dip in ages. And then here you have post 1950 and the ages start to rise again. And you'd say, okay, well, maybe we're getting back on the curve. Well, after 1975, the average age that people first got married, males did, starts to increase dramatically. And we could argue, in fact, that it's continuing that trend, at least for now. But I don't think we're going to expect people to have their first marriage at, say, the age of 80. So this regression will work over a range and within the data that it's used. So we can't assume that the relationship between X and Y won't change outside of our observations. And if you have to extrapolate into the future, at least don't believe that your prediction is going to come true. Now let's go ahead and take a look at outliers, leverage, and influence. So an outlier is a point that's far from the body, and it can really have an effect. So here you can see, here's this outlier, and the blue line shows the regression without that data point. And the red line shows the regression with the red data point. So the point is, no pun intended, that this puppy right here is dragging the whole line. Even though there are a lot of points on this regression and it looks pretty good, that one point is actually dragging the line up. So it's having a big effect. So the linear model doesn't fit points with large residuals very well. So this would have a large residual, all right? And it's important to pay special attention to points with large residuals. So when you're looking, remember, you want to look at the residual plot. And if there's a large residual, pay attention. A data point can also be unusual if its X value is far from the mean. What does that mean? That means it's either way to the left on the graph or way to the right. So these are called high leverage points. And they have the potential also to change the regression line. And we say a point is influential if omitting it from the analysis gives a very different model. So let me show you what we mean here. So this point, you have all these points scattered here, and you're like, well, there's no pattern. That looks pretty strange. You throw one point out here, and all of a sudden you've got a correlation, right? Or you throw the point down here, and you've got a correlation. So having a data point that is a single data point just far to the right or far to the left, that can really have an impact. You can't really just delete these points from data, but you can try to model the data with and without these points. And you should discuss both regression models to understand why there is a difference. When I worked in analytical instrumentation, we would often be looking at, we would be creating a regression, usually linear, sometimes not. And we would be looking at these points that were far from the data. And sometimes what we had to do is say, is there a reason that that point is influencing it? For example, if I was trying to analyze phosphorus in a sample and it had a high sulfur content, that can really influence the point. And basically add extra what look like phosphorus X-rays to it, because phosphorus and sulfur are similar or close together on the atomic table. So anyways, whenever sometimes we had to do a fit and delete a point, and we would say the fit with and without the point, and the reason we thought we could delete the point. So we have to be very careful when trying to omit data. Otherwise, I could just go through here and cherry pick, say, let me get rid of that one and these, and then get a really beautiful line that means nothing. So we don't want lines that mean nothing. So here's some warning about influential points. They can actually hide in the plot of residuals. So looking at the plot of residuals is not good enough. Why? Well, if they have high leverage, they're pulling the line close to them. So the residual is not going to be very big. All right. You'll see influential points more easily by looking at the scatter plots. So always look at both residual plots and scatter plots. Both are important. I know it's extra work. Okay. Almost last but not least, causation. Now, you guys are really good about knowing that correlation does not mean causation. And here's a classic example. We're looking at life expectancy plotted against the square root of doctors per person and square root of TVs per person. Oh my goodness. It looks like TVs cause better life expectancy than doctors. So what we should do is start shipping TVs to all the poor countries around the world, and they will live longer. Actually, there's something else going on here, and that's a lurking variable. That's one that's not on the graph, but might be the real cause of the association. So here, odds are you have more TVs because you have more money. Okay? You can have a lot of doctors, but that doesn't mean there's a lot of money. It's maybe a little bit. So you do see some correlation here. And the more money you have, the better you tend to have better health care, you eat better, you don't have to have as tough work, hopefully. Anyways, but you get to live longer. So the real lurking variable in here is wealth. Now let's go ahead and take a look at working with summary values. So we got a couple different topics in here. Instead of working with individual data points, we can work with the mean. So what I could do is take a bunch of, take the average for people, weight for people who are 64 inches tall, average weight for people who are 68 inches tall. And then when I plot the means instead of the individual data points, you can actually see a stronger correlation. So the reason is when you have summary statistics, because there's less variation, you're going to see stronger correlation. Because remember, correlation explains the amount of variability. Well, at least the R squared does. And the less variability I have in the data, which I'm naturally going to have less when I use means that there's just plain old less variability, so more of it would be explained than unexplained. Now, so first of all, when you're working with it, remember, means vary less than individual values. And scatter plots that use means show less scatter. This can give you a false impression of how well a line summarizes the data. So if you use the mean, remember, you're using the mean, not the individual. So now if you get just summary data, that can actually be a problem because you can't get back to the original data to see how that goes. So anyways, working with summary values, be careful with that. Don't assume that the correlation for summary values is going to be the same as correlation for individual values. So let's quickly wrap up with what can go wrong. Make sure the relationship is straight. Check the straight enough condition that we went over in the last video. Be on guard for different groups in your regression, also in the last video. Consider a different fit for each model, or a different model for each group. Beware of extrapolating, especially into the future. Look for unusual points, and they may show up in your scatter plot. They may show up in your residual. You have to look for both. Beware of high leverage points, especially those that are influential. And consider comparing two regressions with and without the unusual points. Treat unusual points honestly. Don't just remove them to get a better fit. Otherwise, I could remove anybody that's really bothering my fit. Beware of lurking variables. Don't assume that association is causation. And watch out with dealing with data that are summaries. Don't assume that your correlation there will work for the general population, because you're working with averages. And for your practice problems in Chapter 9, please do these 3, 5, 7, 9, 11, 15, 17, and 23, and come to class with questions.